Welcome, my dear students and others, to this Chapter 11 continuing coverage of liquids and intermolecular forces. For this one, I'm going to teach you about phase diagrams. So, the figure below is called a phase diagram, which is a graphical way of summarizing the temperature and pressure conditions in which a substance will be a solid, liquid, or a gas. Now, as you can see, a phase diagram kind of looks like a butt. It should make sense then that the area beneath it is a set of conditions at which a substance will be a gas. The right cheek represents the region of temperature and pressure where this substance is a liquid. Super gross, I know. And the left cheek is the region of conditions where this substance is a solid. With that in mind, by way of reminder, this diagram shows us all of the different names of different phase changes. For example, whenever a solid converts directly to a gas, we call it sublimation, and its reverse is deposition, like a legal deposition. Separately, when a liquid converts to gas, which we normally call boiling or evaporation in everyday speak. In thermodynamic terms, we actually call it vaporization, and its reverse is condensation, whereas when a solid converts to a liquid, which in everyday speak we call melting, in thermodynamic speak it's called fusion, which is to me actually confusion, and its reverse, which we would normally call freezing, in thermoterms is called crystallization. In any event, it's very useful to memorize all of the names of these phase change interconversions as we move forward. This is a more detailed phase diagram, again, still looks like a butt, taken from our text referenced in the description below that we're going to take a few moments to analyze. So the point right here where the red curve, this red curve down here, is at 1 atmosphere is called that substance's normal boiling point. That is the place where this substance converts from liquid to gas, that is, it boils at 1 atmosphere, where 1 atmosphere intersects that line of demarcation between liquid and gas. Separately, the place where this red curve ends, way over here, is called the critical point. Beyond this point, liquid and gas phases are indistinguishable, and the substance is said to be a supercritical fluid. Now let's zoom in on the green line down here. This green curve way down here shows the equilibrium between solid and gas phases. Zooming up to the blue curve right here, which is kind of a straight line in this butt diagram. This blue curve is the melting curve. It shows the equilibrium between solid and liquid phases. Increasing pressure, as you can see in this particular diagram, because it's kind of angled to the right, usually favors more and more solid. Thus, if you push more pressure down on a substance, it will lock those molecules down to keep them solid. So, in such increased pressure state, you'd have to increase temperature in order to melt it. The melting point at 1 atmosphere pressure, that is where 1 atmosphere line intersects that melting curve, is called the normal melting point. Now, point T of this diagram right here, where the 3 curves intersect, is called the triple point, where all 3 phases are in equilibrium, solid, liquid, and gas. Any other point on any of these 3 curves represents an equilibrium between just 2 phases. That magical triple point is very special indeed. That takes us to a beautiful example question. The phase diagram of a hypothetical substance is shown right here, taken from our text referenced in the description below. I want you to estimate the normal boiling point and freezing point of this substance, and then separately figure out what is the physical state, solid, liquid, or gas, of this substance under each of the listed conditions here. I'm not going to do this for you, but I invite you to try this on your own. We end then with liquid crystals. So some substances can exist under certain pressures and temperatures in a state that is somewhere in between liquid and solid. This state is called a liquid crystal state. Liquid crystals are often used as pressure and temperature sensors in devices such as digital watches and laptops, as well as touch screens on tablets and phones. Now, they can be used in these devices because the weak intermolecular forces holding their molecules together in the crystalline phase are easily affected by changes in temperature, pressure, and electric fields. You can see then that they're very useful. So there are different types of liquid crystals as shown in this figure taken from our text. For you, my university students, I only show you these so that you can appreciate how cool they really are. And when I say cool here, I mean, awesome. I don't mean temperature-wise. So for my students in my class, you do not need to memorize their names or structures. I just want you to see them. You can also answer one or more of our problem set questions by using the figure shown right here. That then is the end of our Chapter 11 coverage. Thank you so much, my dear students and others, for going through this journey with me. Until I see you again then, please have an enjoyable and wonderful rest of your day.